Hello everyone. Today we are going to analyze this beam using moment distribution method. Before analyzing, let's see the beam one time. In this beam, there are two spans, span AB and span BC. In the span AB, there is uniformly distributed load 24 kN per meter acting for the full span. In the span BC, there is a point load 50 kN acting at 2 meter from the point B. In the point A, there is a fixed support. In the point B and in the point C, there are roller supports. Span AB is 4 meter long and span BC is 5 meter long. In this analysis, we have to calculate three moments. In the fixed support, there will be a moment. Here, the moment is MAB. In the joints, there will be two moments. In the joint B, there are two moments, MBA and MBC. In the point C, there will be no moment because it is the simply supported end. So, MCB is equal to 0. So, in this beam, totally we have to find three moments, MAB, MBA and MBC. Also, we have to find three vertical reactions, RA, RB and RC. Now, let us calculate the fixed end moments. For calculating the fixed end moments, we have to assume every span as a separate fixed beam. First, let us take the span AB and assume that it is a separate fixed beam. Now, let us see the formulas to calculate the fixed end moments. In this table, you can see some of the important fixed end moment formulas for the different type of loadings. In the span AB, there is UDL acting for the full span, so we have to select this condition. The formulas are minus WL square upon 12 and positive WL square upon 12. In the span BC, there is a point load which is not acting on the center, so we have to select this condition. The formulas are minus WAB square upon L square and positive WA square B upon L square. Now let us apply those formulas and find out the fixed end moments. M of AB will be negative because it is acting in the anticlockwise direction. M of BA will be positive because it is acting in the clockwise direction. In the span AB, UDL is acting for the full span. We already saw the formulas minus WL square upon 12 and positive WL square upon 12. Here W is 24, L is 4. When we apply the values inside the formula, we are getting M of AB is equal to minus 32 kN meter and M of BA is equal to 32 kN meter. Now let us calculate the fixed end moments in the span BC. In the span BC, there is a point load 50 kN. It is not acting on the center. We have already seen the fixed end moment formulas. Let us apply the values inside the formulas. W is 50, A is 2, B is 3, L is 5. After calculations, we are getting M of BC is equal to minus 36 kN meter and M of CB is equal to 24 kN meter. In the moment distribution method, we have to calculate the distribution factor. We have to calculate the distribution factor values only in the joints because in the ends we can easily say the distribution factor values. In the point A, there is a fixed end. In the fixed end, the distribution factor will be 0. So the distribution factor for AB is 0. In the hinged or roller supported ends, the distribution factor will be 1. In the point C, there is a roller supported end. So the distribution factor for CB is 1. In this case, we have to calculate the distribution factor only in the joint B. To calculate the distribution factor, we have to find the stiffness. Let us see the formulas to calculate the stiffness in the joints. If the fair end is fixed, the formula is 4EI upon L. If the fair end is hinged or with a roller support, the formula is 3EI upon L. If the fair end is continuous, the formula is 4EI upon L. Using those formulas, let us calculate the stiffness values in the joint B. From the joint B, we have to calculate two stiffness values for BA and for BC. First, let us calculate for BA. For that, from the joint B, we have to look at the point A. In the point A, there is a fixed support. If the fair end is fixed, the formula is 4EI upon L. Length of BA is 4 meter. Let us apply that. Finally, for the stiffness of BA, we are getting EI. Now, let us calculate the stiffness for BC. For that, from the joint B, we have to look at the point C. In the point C, there is a roller support. If the fair end is with roller support, the formula is 3EI upon L. Length of BC is 5 meter. Let us apply that. Finally, for the stiffness of BC, we are getting 0.6 EI. Now, let us calculate summation of stiffness. In the joint B, we have calculated two stiffness values. Let us add both of them. After adding, we are getting 1.6 EI. Now, let us calculate the distribution factor. The formula for distribution factor is K upon sigma K. For BA, K is EI, sigma K is 1.6 EI. When we apply the values inside the formula, we are getting 0.625. For BC, K is 0.6 EI, sigma K is 1.6 EI, sigma K is 1.6 EI. When we apply the values inside the formula, we are getting 0.375. Now let us start making the table. In the table, first let us enter the members. Then let us enter the distribution factor values. We know that in the fixed end, the distribution factor will be 0. So the distribution factor for AB is 0. In the roller and hinged ends, the distribution factor will be 1. In the point C, there is a roller supported end, so the distribution factor CB is 1. In the joint B, we have calculated two distribution factor values for BA and for BC. Let us apply them. Then let us enter the fixed end moments. In the point C, there will be no movement because it is the simply supported end. So MCB is equal to 0. In the table, we have to make CB 0. For CB, the fixed end moment is 24. When we add minus 24 with this 24, it will be 0. So we have released CB and we have to give the carryover from CB to BC. Half of minus 24 from CB will go to BC. Minus 24 upon 2 is minus 12. Now let us calculate the adjusted fixed end moments. For AB and BA, there is no change. For BC, we have to add these two values. After adding, we are getting minus 48. Now let us make the first distribution. The distribution can be done only in the joints. In this analysis, there is only one joint, that is joint B. For the joint B, the members are BA and BC. For BA, the fixed end moment is 32. For BC, the fixed end moment is minus 48. For making the distribution, we have to add these two fixed end moments. Then we have to multiply with the distribution factors. First, let us make the distribution for BA. For that, we have to add these two values and then multiply with the distribution factor at BA. When we do that, we are getting a negative value. Since we got a negative value, we have to enter inside the table as positive. Now let us calculate the distribution for BC. For that, we have to add these two values and then multiply with the distribution factor at BC. When we do that, here also we are getting a negative value. So we are entering inside the table as positive. Now we have to make the carryover. We cannot make the carryover between BC and CB because we have already released CB and made it 0. Only between AB and BA we can make the carryover. For AB there is no distribution, so we cannot make the carryover. From BA, half of 10 will go to AB. 10 upon 2 is equal to 5. Let us apply that. Now we can't continue this problem any further. In the joint B only, we can make the distribution. But for BA and BC, there are no values. In this case, we cannot continue. So let us add the values and find the final moments. We have to add the values from the adjusted fixed end moments. That is why I have made this color line. We have to add the values below this color line. When we add these two values, we are getting minus 27. When we add these two values, we are getting 42. When we add these two values, we are getting minus 42. So in this analysis, we have calculated all of the moments. In this analysis, we have calculated all of the moments. For MAB, we got a negative value. That means MAB is acting in the anti-clockwise direction. For MBA, we got a positive value. That means MBA is acting in the clockwise direction. Finally, for MBC, we got a negative value. That means it is acting in the anti-clockwise direction. Now, let us calculate the reactions. First, let us take the span AB and calculate the reactions. In the span AB, there are two movements, MAB, which is acting in the anti-clockwise direction, and MBA, which is acting in the clockwise direction. In this span, first I am going to calculate RA. For that, I am going to take movement about B. In this case, I am moving towards right hand side. Clockwise will be positive and anti-clockwise will be negative. The vertical reaction RA is acting towards the point B in the clockwise direction, so it will be positive and the distance is 4 meter, so 4 RA. The UDL is acting towards the point B in the anti-clockwise direction, so it will be negative. For the UDL, we have to multiply with the distance and distance by 2, so 4 into 4 upon 2. Then there are two movements. The moment 27 is acting in the anti-clockwise direction, so it will be negative. The moment 42 is acting in the clockwise direction, so it will be positive. After the calculations, we are getting RA, which is equal to 44.25 kilonewton. Now, using the rule, summation of vertical forces is equal to 0, we can calculate RB1. Here there are two upward forces, RA and RB1. They will be positive. The UDL is acting downwards, so it will be negative. In the case of UDL, we have to multiply with the distance to get the total load. Here we can apply the value of RA, which we already calculated. In this way, we can calculate RB1, which is equal to 51.75 kilonewton. Now let us take the span BC and calculate the reactions. In the span BC, there is only one moment. MBC, which is acting in the anti-clockwise direction. In this span, first I am going to calculate RB2. For that, I am going to take moment about C. RB2 is acting towards the point C in the clockwise direction, so it will be positive and the distance is 5, so 5 RB2. The point load 50 kN is acting towards the point C in the anti-clockwise direction, so it will be negative and the distance is 3. Then we have one moment 42 which is acting in the anti-clockwise direction, so it will be negative. After calculations we are getting RP2 which is equal to 38.4 kN. Now let us apply the rule summation of vertical forces is equal to 0 to calculate RC. RB2 and RC are acting upwards, so both of them will be positive. 50 kN is acting downwards, so it will be negative. Then let us apply the value of RB2. Finally, we are getting RC which is equal to 11.6 kN. In the point B, we have calculated the reaction 2 times. Let us add both of them. After adding, we are getting RB which is equal to 90.15 kN. Now we are going to draw the shear force diagram. Before drawing the diagram, let us calculate the shear force values. I am going to calculate from the point A and towards the point C. In this case, I am moving towards right hand side. Upwards will be positive and downwards will be negative. You can see the calculations. Using the values, we can make the shear force diagram. Now let us make the bending moment diagram. For the bending moment diagram, first we have to make the free moment diagram, then end moment diagram. For the free moment diagram, we have to assume every span as a separate simply supported beam and calculate the moments. If in the simply supported beam, UDL is acting for the full span, the formula for the maximum bending moment is WL square upon 8. Here W is 24, L is 4. When we apply the values inside the formula, we are getting 48. In the span BC, there is a point load. This point load is not acting on the center. The formula for the bending moment is WAB upon L. Here W is 50, A is 2, B is 3, L is 5. When we apply the values inside the formula, we are getting 60. For the UDL, the diagram will be in the shape of a parabola. For the point load, the diagram will be in the shape of a triangle. Now let us see how to make this end moment diagram. For making the end moment diagram, we have to arrange the moments in the clockwise and anti-clockwise directions. Then using the curves, we can make the diagram. We have to see the direction of the arrows. All the arrows are indicating upwards. That means the end moment diagram comes above this line. Then using these values, we can make this diagram. In the point B, there are two movements. Even though there are two movements, we have to mark only one point because both of the arrows are indicating upwards. That means they indicate only one point. If the end moment diagram comes above this line, that will be negative. If it comes below the line, that will be positive. Right now, all of the values are coming above the line, so it will be negative. Now, let us combine the free moment diagram and end moment diagram and make the bending moment diagram. Wherever they are acting alone without mingling, we can mark the values with the signs. Here the end moment diagram, here the free moment diagram, end moment diagram, and finally the free moment diagram. Wherever they are acting together, we are not marking anything, we just keep the space empty. Now we are going to end this session. Thank you for watching this video.